In this video, we're going to continue our discussion of power series functions. Find the power series representation of the function f of x is equal to tan minus 1x, and also find the radius of convergence. Question 1b, express pi as a sum of an infinite series by using the result of exercise 1a. And 1c, evaluate the integral tan minus 1 of x squared dx as a power series. Let's start with part A. So we have f of x is equal to tan minus 1x. The first thing we notice is that a derivative of tan minus 1x is equal to 1 over 1 plus x squared. And we would like to find a power series representation of arctangent of x. So tan minus 1x, we can write this as the integral of 1 over 1 plus x squared dx. Now let's think about this for a moment. We're looking to find the power series representation of tan minus 1x, of this function. We're writing it as an integral of a sum of a geometric series that can be expanded term by term and integrated term by term. How is this the sum of a geometric series? Because it can be written in the form 1 over 1 minus r. So we have tan minus 1x is equal to integral 1 over 1 plus x squared dx, and we can rewrite the integrand as 1 over 1 minus x squared. Minus x squared is a common ratio of the geometric sum. All right, so now we have rewritten the integrand as a sum of a geometric series. So we have 1 over 1 plus x squared. We write this as 1 over 1 minus x squared. Now the first term is 1 multiplied by the common ratio to get the next term. 1 minus x squared times minus x squared plus x to the 4th minus x to the 6th plus minus and so on. And absolute value of x is less than 1. That is the radius of convergence of this geometric series. Now tan minus 1x is the integral of 1 over 1 plus x squared dx. And this integrand is a sum of a geometric series that we have expanded term by term, and hence we can integrate term by term. So we have integral 1 minus x squared plus x to the 4th minus x to the 6th, and so on. We integrate this with respect to x. So tan minus 1x is equal to integral of 1 is just x. Integral of minus x squared gives us minus x cubed, divide by 3. Integral of x to the 4th, reverse the power rule, add 1 to the exponent, divide by the same. X to the 5, divide by 5, minus x to the 7, divide by 7, and so on. Of course, plus c. All right, we can rewrite this in a summation notation. Tan minus 1x is equal to constant c plus summation n equals 0 to infinity minus 1 to the power of n. And we see odd powers. We see 3, 5, 7. So to generate odd powers, we use 2n plus 1. That's how we do the pattern recognition. And it's always being divided by the same number. So we got x to the 7 divided by 7, x to the 2n plus 1 divided by 2n plus 1. Now we need to find c, the constant of integration. So we have tan minus 1x. Tan minus 1x is equal to c plus summation n equals 0 to infinity minus 1 to the power of n, x to the 2n plus 1 divided by 2n plus 1. Plug x equals 0 into both sides. So we get tangent minus 1 of 0 is equal to c plus n equals 0 to infinity minus 1 to the power of n, 0 to the power of 2n plus 1, so all the terms will end up being 0, divided by 2n plus 1. So we get tan minus 1 of 0 is equal to c plus 0. Because all the terms are 0, this whole sum is going to be 0. What is arctangent of 0? What is the angle whose tangent is 0? That is, of course, 0. So 0 is equal to c. That's the constant. We have found the constant of integration to be 0. So tan minus 1x is equal to summation n equals 0 to infinity. We have found the power series representation of tan minus 1x. That is going to be negative 1 to the power of n, x to the power of 2n plus 1, divided by 2n plus 1. Now let's look at the radius of convergence of the power series for tan minus 1x. The original series, 1 over 1 plus x squared, that was actually the integrand that was integrated to produce the power series for arctangent of x. This original series is a geometric sum, so we rewrote it as 1 minus x squared. And the common ratio of this geometric series is minus x squared. A geometric series converges when the common ratio, the absolute value of the common ratio, is less than 1. So absolute value of minus x squared is less than 1. Absolute value gets rid of the minus sign, and x squared is always positive, so we can rewrite this as x squared less than 1. Square root both sides, and we get absolute value of x is less than 1. So the radius of convergence of the new series tan minus 1x is equal to summation n equals 0 to infinity minus 1 to the power of n, x to the power of 2n plus 1, divided by 2n plus 1. The radius of convergence of this new series is the same as the original series that was a geometric series. So that's what we learned earlier, that when we integrate a power series, the radius of convergence does not change. And because the original power series was a geometric series where the radius of convergence was 1, the new series, tan minus 1x, has the same radius of convergence. All right, part B. Now, in this case, we want to find pi. So we're simply going to plug in x equals 1 into the power series for tan minus 1x. So we have tan minus 1x is equal to summation n equals 0 to infinity minus 1 to the power of n, x to the power of 2n plus 1, divided by 2n plus 1. Let's plug in x equals 1. So we get tangent minus 1, arctangent of 1, is equal to summation n equals 0 to infinity minus 1 to the power of n. Now plug x equals 1 in here. 1 to any power is just 1, so we don't need to write that. Divide by 2n plus 1. Now if we expand this, plug n equals 0, we're going to get 1. Plug n equals 1, we get negative 1/3. N equals 2, we get plus 1 over 5, minus 1 over 7, and so on. So what is arctangent of 1? What is the angle whose tangent is 1? That is pi over 4. Arctangent of 1 is equal to pi over 4. So pi over 4 is equal to summation n equals 0 to infinity minus 1 to the power of n divided by 2n plus 1 is equal to 1 minus 1/3 plus 1 over 5 minus 1 over 7, and so on. We would like to find the series representation, the infinite series representation of pi. So we have to multiply both sides by 4. So pi, we get pi is equal to, and multiply by 4, we get 4 times summation n equals 0 to infinity minus 1 to the power of n divided by 2n plus 1. Multiply both sides by 4, so we get 4 times 1 minus 1/3. So we now have an infinite series representation of the number pi. That means that the more of these terms that we add up, the closer we get to the exact value of pi. Of course, the entire infinite series is the exact value for the number pi. All right, so now let's look at part C. Part C asks us to evaluate integral of tangent minus 1 of x squared dx as a power series. Now, we already know the power series for arctangent of x. We found that earlier in part A. Tan minus 1x is equal to summation n equals 0 to infinity minus 1 to the power of n, x to the power of 2n plus 1, divided by 2n plus 1. Now, let's plug in x squared for x so we can find the power series representation of the integrand tan minus 1 of x squared. So tan minus 1, arctan of x squared, is equal to summation n equals 0 to infinity minus 1 to the power of n, x squared, to the power of 2n plus 1, divided by 2n plus 1. So we get tan minus 1 of x squared is equal to summation n equals 0 to infinity minus 1 to the power of n. Doing some simplification, we get x to the power of, we have 2 times 2n plus 1, 4n plus 2, that's the exponent of x, divided by 2n plus 1. We have now found the power series representation of the integrand. We can now integrate term by term and get a power series representation of the integral of tan minus 1 of x squared. So the integral of tan minus 1 of x squared dx is equal to the integral, and the integrand now has a power series representation, so we can just integrate that term by term and find the power series representation of the integral. Summation n equals 0 to infinity minus 1 to the power of n, x to the power of 4n plus 2, divided by 2n plus 1. And we're integrating with respect to x. Now, we know that integral of a sum is sum of the integrals. So we reverse the order of integration and summation. So that's going to be equal to summation n equals 0 to infinity, negative 1 to the power of n, divided by 2n plus 1. The only thing that gets integrated is a term that involves x. The rest is a constant that just goes in the front. So integral of x to the power of 4n plus 2 dx. Notice we didn't expand it term by term like we used to. This way is much more efficient because we can just get a closed form for the new integral, for the new integral tan minus 1 of x squared dx. All right, so what we have is integral tan minus 1 of x squared dx is equal to summation n equals 0 to infinity, negative 1 to the power of n, divided by 2n plus 1, integral x to the 4n plus 2 dx. So integral tan minus 1 of x squared dx is equal to summation n equals 0 to infinity minus 1 to the power of n divided by 2n plus 1. Reverse the power rule, integrate this, we get x to the power of 4n plus 3, add 1 to the exponent, divide by the same, 4n plus 3, plus c. So notice working with this idea of integrating the sum and reversing the order of summation and integration is far more efficient than trying to recognize the pattern later on, because it gives us the pattern just through the calculations that we do. And we now have the integral of tan minus 1 of x squared dx as a power series representation. Of course, we can expand this term by term just to show, just to express this as a power series. So tan minus 1 of x squared dx. Let's plug in n equals 0, and we're going to get, let's put the constant c first. Plug n equals 0, and we're going to get x cubed. Divide by 3. N equals 1, we get minus x to the 7. Divide by 7 times 3. And put n equals 2, we're going to get x to the power of 11 divided by 11 times 5. N equals 3, we get minus x to the power of 15 divided by 15 times 7. Of course, this is an infinite series. It goes on and on. So the power series, we have found the power series representation of tan minus 1, of the integral of tan minus 1 of x squared dx. And the radius of convergence of this new series is the same as the radius of convergence of 1 over 1 plus x squared, the original series that we worked with. And the radius of convergence of this is just 1, because we rewrite this as 1 minus x squared. And this is a geometric series with radius equal to 1. So the radius of convergence of the new series is the same as the radius of convergence of the original series, which was a geometric series. All right, thanks.